So this is the last part of the series of the lectures. So this time the topic again will be quite advanced. We are going to be talking about scaling computations using parallel computing. So how to scale out your Julia computations. This is a unique feature of the language that it has really lots of functionality built into to scaling and running really big Julia programs. But before that, we'll start with discussing the homework for the MIT students. So this is a course. This is the course that is aimed for MIT students, and for MIT students, this is graded. This is only for MIT students, not for other participants. And we have the following two simple tasks. So the task number one is to perform an analysis of the data. You have here information about creating some simple data as a vector and then somehow transforming in such a way in order to build a plot and build a model. Not complicated. Our instructions are given here. Should you have, of course, any questions, just don't hesitate to let us know. So this is the homework number one. So you perform the analysis of the data. The text of the homework is also available at the course website. So if you download the slides of this presentation, you will find it there. So you do not have to take the exact notes. And there is the second task. And the second task is about building a simple optimization model. So you need to optimize production in factory. Now all assumptions again are given. You build an optimization model using Julia Jump, and you send us the solution. So how to send the solution? So we kindly ask you to make either a Jupyter notebook or a file with Julia code, but also please provide all the comments that are required, just as comments in the Jupyter notebook, as text, as markdown text in Jupyter notebook, or simply as comments in the source code. So please provide the source code together with the description. It's up to you whether you use Jupyter Notebook to send the homework or just plain Julia files. We'll be okay with both of them. And here's the email address to sending the homework. The deadline is 1 week from now. So you have 1 week to make this two simple homeworks. Should you have any questions, also do not hesitate to contact us. Last but not least, this is only for the MIT. So this course is being streamed. The homework is for the MIT students only. Are there any questions regarding the homework? I see at the classroom, nobody has any questions. And if you have any questions, or if some MIT students are participating online and you want to ask something, just don't hesitate to ask on chat. We are monitoring it. So, if you have some questions, if something is not clear, let us know. We're also reachable by email should you have any problems and so on. Also, please do not hesitate to contact us. So this is all regarding the homework. So now I'm going to move back to scaling computations. So why do we need scaling of computations? Typically, when we run a computer program, we use a single CPU and a single machine and a single set of computations. And this is very common and quite sufficient for many applications we can think of. So if I have in my machine, I have a tool such as a task manager. I can see that my machine has something like 16 logical cores, and perhaps it could be doing something at 60 processes at the same time. If we're writing standard software, standard program, we are usually using only one out of all those cores. So essentially, we are not using the full capacity of our operating system. And the goal of parallel computing is to use full power of a single computer, or to make it even more complex, to combine several machines, to combine several computers into a computing cluster. We'll have a look on what technologies Julia has for that. More specifically, we are going to have a look at several options for parallelizing of processing in programming languages. And there are a few approaches. And we go through all of them with except for GPU computing. We have only slightly less than 2 hours, so there will be no time to discuss GPU computing. But other than that, we'll discuss the following approaches. So one is single instruction multiple data. So this is a SIMD. So this is the feature of processors of CPUs, that in one processor cycle, several operations can be made. Like a CPU has a registry, and into the registry, not only pairs of, suppose you are making an operation of addition or operation of multiplication. In the CPU register, you can add not only a single pair of values, but several pair of values, and perform addition or multiplication within one CPU cycle, within the same set of CPU cycles. So if I design my code program in this way, that this is possible, I can get a speed up basically for free. I do not need to use more power of CPU, more electricity, more of anything. Just I can perform several operations within a single CPU cycle instead of one. We'll have a very simple look on how this is supported in Julia. Then we have something which is named green threads, which are coroutines. This is a good place where the I/O stands for input/output, is the bottleneck. And the idea behind green threads is that if I'm reading a file, the same thread could be do something else in the meantime, because I/O operations, input/output operations are blocking. You need to wait for resources. So you need to wait for disk to spin or SSD disk to provide data. You need to wait for the internet connection and so on. So basically, when you're, for example, downloading a file from the internet, your CPU is idle. You do not use CPU, and this can be used for something else in the meantime. And using this technology is called green threading. This is available also and quite popularly used in Python. But actually in Python, this is the only threading mechanism available. Then we have multi-threading. So multi-threads are kind of threads are kind of tasks within a process that can be executed on different logical cores. So I can have one Julia process running, but I can further this process to utilize several cores. So this is multi-threading. And this is available in two ways, let's say in two ways in Julia. So one is via the Julia language. So I can write code in Julia that is multi-threading. So I can write the code that is using this functionality. Multi-threading is also possible via libraries. So some of the libraries of the Julia ecosystem are multi-threaded. Some even have a separate control, like we have BLAS library for numerical computations, and you can configure it to use a single thread or multiple threads. Also, several Julia packages such as aforementioned data frames are being developed to using multiple threads. So this can be on the level of libraries, but of course the language is also designed in a way that it can handle several threads at the same time. So multi-threading has its advantages and disadvantages. Maybe we'll slightly try to discuss them. But there is another level. This is multiprocessing. So what is multiprocessing? I can run, instead of a single Julia process, I can run several Julia processes at the same time and have divide the job into chunks, divide these jobs into small parts, and I can have each of those processes to do a different part of the job. So this is again something we can log. And You can do multiprocessing on a single machine, on a single computer, but you can also do it on computing clusters. And Julia supports it in a very nice way from moving from running your software, running your Julia program on a single computer, onto running the same program on a computing cluster. We do not have enough time here to build live a computing cluster, but we'll discuss some basic assumptions that you need to do there at the end of presentation, so there won't be then probably too much time to discuss those assumptions in great detail. But basically, you can combine a set of machines into a Julia cluster. This is known to work in the cloud, such as AWS. This is known to work in supercomputers such as Cray supercomputer. Okay, so these are the area when you can scale out computations. Of course, you try to do those things when your computing times are not sufficient. So when you are not happy about how fast your computing is being performed. So we are starting to discuss with the first approach, which is single instruction, multiple data. So this is a feature of Intel processor, and uh, uh, modern CPUs have multiprocessing element, and they can at the same time they can perform several operations. Now this is data parallelism rather than instruction parallelism. So this is called single instruction multiple data. So on all sets of data you need to perform exactly the same instruction. So all number pairs need to be added, or all number pairs need to be multiplied. So it must be the same operation, the same instruction, but on different sets of data. So let us have a look how this is going to be. And now, of course, we need to start the Jupyter notebook. Now, since we will be doing multiprocessing, there is a small difference how we need to start the Jupyter notebook compared to previous lectures. So what do we need to do? We of course need to have the command line. So here I'm already at the folder where my files and my Jupyter notebooks are. So I'm starting Julia as we did always. Now, depending on your Julia package configuration, you might, being in the main folder, you might want to activate it. So let me do that. So this was already done a few times. So using package J, activate the current folder. This was quite obvious. Now, before, so I allowed iJulia, of course, now I can allow iJulia, but now, before I run Jupyter Notebook, I need to tell Julia to run in multi-threaded mode. There are many ways to do it. There will be also a slide showing all the possible ways to do it, but we do it via environment variable. So we now set the environment variable. We'll do it from Julia. You could do it. You could do it also before starting even the initial Julia, because the environment variable are being propagated in the operating systems as the processes are being forked. Okay, so you have parent process, and if you set somewhere the environment variable, the child process and grandchild process and so on of that parent process is going to see that environment variable. This is how it works. So we are going to set this environment variable, and this environment variables are available in Julia via the special and global variable. And this variable, and you have this also on the slides, is Julia underscore num threads. So this is the number of threads that will be used by child Julia processes, and I'm going to set that for 8. Once I do it, this is the number of threads that will be seen by Jupyter Notebook. This is one of many possible ways how to do it. We could, for example, we could use Julia comments to edit the Jupyter configuration, or create a new definition for a new Jupyter kernel. So there are many ways to do it, This one seemed for me to be the simplest, okay, because it's maybe also most straightforward. So this is what I'm going to do. So I'm executing this command simply to set, yep. So given current computers, I would say this is good value for everybody. I assume you do not have usually less than 8 threads in any modern computer. On the other hand, this is just for experimentation. I would say this is good for everyone. Basically, you can see how many. So Julia supports the number of threads up to the number of logical cores. So you can see how many, a task manager, depending on your operating system, like HTOP on Linux, how many logical processes you have. So I have here 16 logical processes, so 8 is okay for experimentation. Okay, there is always, of course, a question on how many you should set. Also, it's worth knowing that if you have huge machines, like you have a machine with 128 logical cores, then basically setting over something like 16 or maybe 32 threads does not always necessarily brings performance boost, and you would rather want to look at multiprocessing. If you have too many threads, then there is a mechanism of switching between the threads, and the performance, the increase of performance is becoming discussable. And okay, it's 8. I assume it should work for everyone. Okay, and now once I've said this, then now I can run Jupyter Notebook. So this is Notebook and the current directory. Okay, and this will launch me the Jupyter Notebook. So once I launch the Jupyter Notebook, I'm going to see the screen that you know very well. So with all those, I'm going to see the screen with all those messages. I have said that Julia threads to 8, and I have launched. Of course, I have launched this just before the lecture, so I have just switched the screens, as you can see. But here it is. So this is Notebook, dear, and this has been launched. Launching the Jupyter Notebook, of course, has started me the web page with the course materials. And here in the course materials, you can see 4B scaling computations using parallel computing, and this is it. Now, we want to check if we did it correctly. So the first instruction in the Jupyter notebook is println number of threads that the Julia is run, and I'm here inserting the command inside the string threads and threads. So this yields the number of threads that my Julia is configured. And if you did everything right, you should be seeing 8. Of course, you might have made a typo. If you made a typo by typing the environment variable name, then you are not seeing 8. Simple as that. Okay, so this was about the multi-threading configuration. We do not need this for SIMD. So SIMD is single instruction, multiple data. We'll be needing multi-threading slightly towards the middle of the lecture, but I didn't want to make you all, to switch Jupyter Notebook. So you all have the chance to run the same. So we start first with single instruction, multiple data. So we have two versions of the code. So this is a simple code that makes a dot products over two vectors. Now we use here a special macro that is named inbound, and this macro is disable bound checking. Okay, so if you are accessing a vector, normally a bound check is being performed. So it is being checked whether you are within or not within vector. This takes time. And this also means that the assembly code, that the code that is generated for the CPU, needs each time the variable is accessed. There's some condition that check if we are not out of bounds by accident. So we turn it off. It slightly increases the performance of the function, but it also allows to disable forking in the code, in the machine code, forking with regard to checking the bounds for variables. Which means that this code is possible, that it will be possible to use this code with single instruction, multiple data. Okay, so here I'm defining this function. So this is the function .1. And since this function is making only simple algebraic operations, so this is a simple code, and since I disabled bounds checking, so there is no forking, there are no if instructions in the code or anything similar, I can tell Julia compiler to parallelize to increase the code efficiency by using single instruction multiple data. And now using SIMD is as simple as typing SIMD in front of your loop, but it will not work with every code because the code needs to meet several properties to be SIMD friendly. Also, there are other Julia libraries that might be helping with that, like for example, loop unrolling, so changing loops into sets of instructions and so on. But basically, it won't work like magic for every code. But this simple code is just doing lots of multiplications for pairs of values and then aggregates them. This kind of code is quite perfect for simple instruction multiple data. Okay, so I have generated the second function. So now I can generate myself some test data, and I have two pieces, and I have so this is my test data, and I can write so I'm generating x and y. So these are two some vectors or some floating point numbers, and now I could write something like result 1 equals at benchmark on edge b time if you want something shorter, dot 1 and those vectors. We'll be making here quite a lot of code benchmarks. The benchmark macro as well as the b time macro, they both have they are both using those dollar sign, and those dollar sign here are used for variable interpolation in this way that if I have local variables, they might be not type stable, so the Julia compiler might not know what is the type, and it might be problem with micro benchmarks. It might affect the benchmarking time, which normally you do not want to have. So that's why when we are using some external variables in benchmarks, we must make sure they are kind of local variables to the benchmark that we run, and this is achieved via the dollar sign. So here is the test number 1, and in the same way, we could make the test number 2. So the test number 2 will be dot 2. The code you have Jupyter Notebook was just doing b time, it would just yield time, but I thought it might be also interesting to see a full benchmark result. Okay, and you can see that for the most optimistic case, the code that is using SIMD is roughly 8 times as fast as the code that does not use SIMD. And the mean time is something like the mean execution time is around 3 times as fast. Okay, so simply by decorating the loop with add_SIMD, we have increased the speed of execution of our code by several times. We have increased the speed. We have increased the speed by several times. Now let us have a look at results. So we have now two variables, res1 and res2. Okay, that's exactly the same operation. You remember the code was identical. So yeah, so the only difference was this SIMD operator. This is what we saw. Okay, so the only difference was the SIMD operator. So let us have a look at results. Okay, so let us try to write something like res1 equals res2. And then I'm seeing false, and I'm starting wondering what the hell is going on. So maybe let's show those two variables. Let's show res1 and let's show res2. Okay, I'm having a look at those okay, these were not results, but results of trials, because I've given this at the wrong line. Sorry about this. So I want it at benchmark or maybe at B time. Res1 equals this. So I edited the code slightly, and when I improvise, something didn't work the way I wanted, but this will be the same. Okay, so let me just have res1 and have res2. Okay, so I have those two values. The second code is 4 times faster, so this is what we've seen. And now, again, let me try res1 equals rs2. It's still false. So I got two different results, which starts seeming surprising. Let me show those two values. Why am I still seeing here the trial, not the results? Because it's assigned as a local value. Okay. I will just draw like this. Yes. I will just do it like this. So yes. I should. I assign this as local value. But again, so they are still not equal. And let me show those values. And you can actually see that there is a very tiny difference around 13 places after the comma. Okay, so I'm evaluating those two functions with exactly the same arguments, exactly the same values, and I'm getting different results. There's very slightly difference, like 15 places after the comma. Okay, and then so this is what I wanted to show. Then I started to wonder what is. Then I started. Then I'm starting to wonder what is going on with those. What is going on with those test results? And actually, what's happening? The order of addition is different in this code here. So I'm getting different order of addition operators here and different order of addition operators here, because SIMD can decide, so it can group the addition operator. And of course, since I'm adding floating point numbers, and those floating point numbers have been generated by run, so they are very long, I'm losing the precision. So this is a different addition order. So this is something to be aware of, that kind of when you do float number computing, this is not deterministic. This is of course not feature of you, Julia, but the future of how CPUs work, and then these are non-rational numbers in the binary system. This is what we are seeing. So we are losing some precision. So a SIMD code might yield very slightly different results than non-SIMD code, and they are both inaccurate results because we are doing floating precision. So simply it's 64 bits, and this is our accuracy. It's no less, no more. So we can never be fully precise when you do computations on 64 bits floating point numbers. So have just some level of precision for that. Okay, so here it is. So we are seeing this for those two values. And this is about single instruction multiple data. Now we go to the next. Now we go to the next topic, which is green threading. And green threads are threads that wait for some I/O operation. Here for the input-output operation, I will be using the simplest possible example, so sleep comment. Sleep comment is an I/O operation. It just tells us to wait for some time. But of course, it could be reading a file from the internet, opening a file from a machine, and so on. So if I have a comment such as sleep2 and I execute it, you wonder how much long that might it last. It of course lasts 2 seconds, plus maybe some time to compile the comment. Okay, so this is how it works. Now, you could rather launch this comment asynchronously. So you have a comment named @async, that tries to launch an asynchronous job. What's going to happen if I do that? Uh, when I did that, I'm seeing that it has finished by some very small fraction of a second, uh, and and I got something which is task runnable. So there is actually I got a task, a running task of sleeping. It would be nice to have a task of sleeping sometimes, I guess, when you have too many exams. So I have a running task of sleeping that is running somewhere on the side. So let me maybe assign this task to a variable. Okay, and the next time I'm going to check what is going on with the task variable t. This is already done because it lasted 2 seconds. But if I do it very fast, if I manage to do 2 clicks within 2 seconds, then this task T, as you can see, is still status runnable. I managed to do very quick execution of the cell within 2 seconds. So this T is still running, but now already 2 seconds have elapsed. So if I press Control Enter once again, you can see this has already status done. So this allows me kind of detach the task from what am I running at any minute. Okay, so this is how I'm detaching the task. And now you could imagine that you have some jobs. Most of examples in this Jupyter notebook will not be on real data, but this will be patterns for various types of data processing. So my goal was to keep this Jupyter notebook as simple as possible and just focus on the parallelization of processes rather than providing complex use case scenarios. Also, this is my experience that if I put too many use case scenarios, then I'm not able to discuss everything with regard to parallel computing. Okay, so we have here a function do job. And what this function is doing is just generating some value. And this value is stored to run. And then it's sleeping that exact amount. And it's returning the number of the job and the time it slept. A typical such non-deterministic function, you could write a function like this that is opening a connection to a website and downloading website. So for example, via the http.gl interface. Okay, but I just didn't want to do a network spider, but if you did a network spider, would have exactly functions which are quite non-time deterministic. You never know when a website is going to answer. And when you try to download something from a website, you are just sleeping. You are just waiting for it. Okay, so this is this function, and the first thing I'm doing, I'm creating some vector. I'm creating some vector of tuples. So tuples are pairs of values. And undiv, it means I want just any area of memory for that vector. And since I have just requested any area of memory, there is some trash inside it, as you can see. So there is some data maybe from some previous processing. Of course, if I'm requesting it many times, each time I'm going to see totally different trash in the memory because each time I'm getting some different memory area, but it doesn't matter. So there is some piece of trash information there, but I'm going to fill it with my code. So first thing I could do, I could perform those. So suppose I want to do this the run job 8 times. So I have 8 places to fill the array. Maybe I'm visiting 8 websites. And suppose I want to do it 8 times. So of course, what's going to happen if I do job 8 times and each one on average lasts half a second, I'm going to get the result somewhere after 4 seconds. So if I'm going to run it, this time it was 3.3. Of course, if I run it more time, it will be similar. And I'm getting some nicely data into the result vector. Okay, but now I'm starting to wonder, can I run this in parallel? Okay, so these are independent jobs. They are IO intensive. So here I'm just sleeping, but you could imagine I'm downloading a website or maybe opening a file. So these are IO intensive jobs. And maybe I could be running them in parallel. Why not to try? So I start to wonder on how to do such loop. So my first idea is the following. So I have loop. So maybe let me try to start execute each job in the loop asynchronously. Let's see what's going to happen. So I run this. And what we are seeing, what result is holding in the memory? It's trash. Oh God, what has happened? Let us have a look again what the result is containing. Let me add a cell result. Oh, now it's not trash anymore. So it's even more bizarre. So what has happened? I have spawned the processes to collect the data, but before any of those processes completed, I have requested the result. So I'm seeing the version of the result that was true. So some rubbish data of the memory. I'm seeing the version of the result that was true before any of those jobs completed. Okay, so it was true before any of those jobs was completed. Then I waited sometimes because I did my talking, and all of those jobs completed, and now I'm seeing the current version of the results. But of course, usually we do not want to have something like this. We would like to wait enough time before we have a look, before we have a peek at the result variable, because maybe we would like to use for another stage of processing. So when we are launching asynchronous tasks, what we want to do, we want to wait until they all get completed. Is it clear? So we want to wait until all those asynchronous tasks get completed. So how we do that? Maybe we could write some semaphore variables that control it and so on. But fortunately, there is a second macro, which stands for synchronize. So if I'm asynchronizing stuff, usually I then want to synchronize it back. So what's now going to happen? This loop is going, how do you think how long this loop is now going to run? So each task, just to recall, so this val here, each task was a random number, so rand yields a number between 0 and 1, and sleeps for that number of seconds. So what is the time expectancy for this loop to run? What is your opinion? No, it will be no more than 1 second, because these all tasks will be running in parallel. Okay, so all of those tasks are now going to launch in parallel, and it will take as long as the last of all of those 8 tasks gets finished. So it might be that all those 8 tasks are going to take some time to run. So I can expect it will be something like 0.9 seconds. It will be never some very short time, because of course the probability that it will be some short time is low, I should say, because I'm picking 8 numbers between 0 and 1, and the largest one of them is going to be the time of this execution. So let us have a look. So I'm running it. Oh, this time I got slightly, so around 1 second, because there's also some time required to do synchronization and so on. So it could also last a fraction of a second. Oh, and this time, for an example, I got 0.99 of a second. If I'm lucky, I could get. So I can expect, because I'm now parallelizing these jobs, I can expect for this to be lower than 1 second. And we can of course see here how everything lasted. And why it's not like, so the longest values here was 0.57. It probably took some time to synchronize. So whenever you do some kind of parallel computing, then bringing results back might also take time. But here I have value now here 0.99 and the time is slightly over 1 second. So this time it did not take long to synchronize the results. Okay, so you can see how this works. And now here is an example, maybe slightly related to the previous lecture. It's kind of one of those examples that I like. So whenever I look at some new programming language and some asynchronous processing and other stuff, I'm always wondering how a web server is going to look like in that language. So here is some very simple implementation of web server. In my code, it's here commented, and the other line is also commented out. It's not in your Jupyter notebook. I commented it out so I could, when I was testing the Jupyter notebook a few seconds before the lecture. But here how it looks. So it's using socket. So we are using plain socket library. So it's very low level kind of web server implementation. I'm saying starting with the web server, and simply my web server is going to listen on the port 9991. If I launch it, okay, it seems I've already managed to launch that server anyway. You don't have to do that, but what I'm going to do, I'm going just to pick a different part. So maybe I was running a test and it's already, this happens. So I just changed to 1992. So I have a server. So I have now a server listening on this port. I removed these comments here that prevented this to run. So here, when this server can get requests. So now what I might want to do, I might want to run some code that is basically handling those requests. Now, I do not want this code to block this Jupyter cell, so I can still interact with Jupyter Notebook. I want this code to run in the background, so I'm running it asynchronously. Now, this code is running an endless loop, and which gets executed whenever there's accept. So socket accept means a new connection has been created in the server. If I didn't put it async here, this code would block because it would wait for a connection to appear for the server. Okay, so that's why it's asynchronously. So here I'm accepting connection to this web server. And here it's some very simple code. So Sebastian was telling you about that 200 is okay. So it's sending like printing to the socket 200. It's behaving. My code is behaving like web server. We want to cheat a web browser that we are a web server. Actually, we won't be cheating a web browser. We are a web server. So here I'm sending some messages that will be understood by the web browser. So this was at the previous lecture. So the code 200, content type, text, HTML, and it's printing something, what you are going to see in a minute. So I'm going to run that code. So now what is happening? Oh, I need to put here true to continue execution. So you have it correct at your Jupyter notebooks. So once I have running this code, so variable continue, it holds a reference to true, so it will be run as long as this is true. And I have somewhere condition for stopping that. If something, then I'm going to stop it. Okay, so this, I got a runnable task. So this is a task that is now running continuously and handling the request. So let me try to connect to this web server. Now I need to slightly edit the markdown because I changed the code. You don't have to. So this is markdown. So this is a language for documentation. Probably most of you have seen it. I would just change the port number because I used 992. Okay, so this is it. So let me try to click at this link. So when I control click this link, a connection opens on another screen. I didn't edit the URL here. Yeah, this is what's happening if you change the port. So once again, Control Enter. So when I control click this link, you can see that I'm getting the result. So actually, this is a very simple web server. This is evaluating a Julia comment. So that's what I got. I typed 3 plus 4, and I got 3 plus 4, 7. So what is the server doing? If you have, oh, I made the font now too large. If I go back to the server, so what is doing? It was taking the input as a Julia command and evaluate it. So it was doing eval meta parse, and there was the comment, or maybe I slash the line. There is the comment that went to the server. It's not very secure way to the server. It's very easy to hack this kind of thing because it accepts any Julia command. So it would be easy to destroy, but it can, for example, evaluate some expressions. Okay, so you can see it works. I can refresh it. I can add new. It's a web server. It's handling the request. And of course, once I'm bored with listening to this web server, I could stop this process that is accepting. Oh, and here we are seeing what the web browser is sending us. So the web browser is sending GET requests. Also, the web browser is often displaying a tiny icon like you have here. And there's a special request that is named path icon. And that's why you are seeing those requests, because I was connecting with a web browser. So anyway, if I want to stop this code, there is a second URL I made, stop me. And this ever running asynchronous task is now stopped. So this is a very simple this is an implementation of very simple web server, and this is one possible application of one possible application of asynchronous, and maybe I've also chosen it to be somehow complementary with the previous lecture. Okay, so you are seeing how this code can be used in a kind of practical examples. Now, asynchronous processing, so async and sync, which is here used for green threading. So green threading is only applicable when you have blocking I/O. So when you have blocking input-output operations. But for an example, if you want to do computation at scale, so you want to do numerical simulation, some database processing, maybe biological computations, I don't know, protein folding or something else, then you need either multi-threading or multi-processing, because green threading, so this is what we do async, is only good when you have tasks that need to wait for some other resource, like downloading file from the internet. So now we have a look at multi-threading. So we had green threading, and on the slides we have also definition, blah, blah, blah. So now we have multi-threading. Now we first start by comparison of threading and multiprocessing. So threading is about having a single process that can use logical cores, can use CPU cores to perform several tasks at the same time. All those processes, all those tasks are sharing a common memory. So if you are going to define a variable in one thread, it will be visible by other threads, which we are going to see in a minute. Number of threads, at least in Julia, number of threads running simultaneously is limited by the number of logical processor. It can create issues with regard to locking and fault sharing. We'll only here have a look at locking, which is the most common problem when doing multi-threading. We do not have time to look at fault sharing, but basically, when you have many people doing exactly the same thing at the same time, you always have problem. You all know probably when you have been doing group homeworks, and then suddenly two people did the same thing at the same time, and then you need to decide how to combine it, so on. It's always so. So the same is about multi-threading, and we'll show how to handle it. Then we have multiprocessing. So processes are just separate. So these are separate Julia programs. They have, each of them has their separate memory, and they cooperate. So many Julia processes can cooperate to achieve a common goal, but they are totally independent. What is difficult then, because there is no shared memory, unless with some exceptions that we are not going to discuss, but basically there is no shared memory. So we need to somehow decide on how to exchange the data between the processes, and bringing this to another level. Those all processes can work on the same machine, on the same computer, or they can work on multiple computers. And the nice thing about Julia is that there is a common application programming interface, a common API, no matter whether we do multiprocessing on a single machine or whether we do multiprocessing in a computing cluster. And in this case, of course, what we have is distributed computing. Okay, so this is quite the same. Now, all those options, when you are starting Julia, all those options can be configured at Julia command line. All those multiprocessing and distributed computing can be also configured while already a Julia process is running. However, as of today, I think it's bound to change in future Julia versions. As of today, the number of threads is fixed the time you start Julia. So you use -t parameter, or you use the Julia num threads environment variable, which is something what we did. So we have those three mechanisms, and each of these mechanisms has a parameter. So for multi-threading, you provide the number of threads. For multiprocessing, you provide the number of processes, but you can also add them later, and this is what we are going to do. And for distributed computing, one possible way to build a cluster is to provide a machine file. Machine file is a very simple file. It just contains names of servers that are visible in your network and number of Julia processes that you want to run on each server. So this is a very simple text file. But you can also add new processes, local or remote, dynamically. So for example, if you have a Cray supercomputer, then you would be running a single Julia process on some node, and then ask Cray cluster manager to add child processes. Okay, so Julia can cooperate with clusters, with cluster managers such as Slarm, such as SGE, or it can add remote processes in the AWS cloud. So there are many libraries for each high performance computing scenario. Okay, so but this is also supported directly on the command line level. So now we go with threading. So what is difference between a single thread and multi-threading? A normal program is going to run like this, that you have a single thread, you have code, it saves some data, you have some files, and you perform operations. A multi-threading code, on the other hand, is going to run like this, that you have a single process with several threads, they all share code, but they all have access to the same data and the same file and files. And so in the same files on disk, so you can have issues that when multiple threads are trying to access the same files and it's the same data in the memory. So we are starting to having an issue when many processes try to access same data in the memory, and this is something we are going to have a small look into. So this is multi-threading. So let us first start looking what is advantage of this. So I'm now checking the number of threads I have on my machine. As you can see, my Julia process is running with 8 threads. This is not surprising because this is what we did later. You remember, we did env Julia num threads equals 8 just before launching the Jupyter notebook. So that's why we are seeing here we have 8 threads. So now we have very simple function. We have a function that is calculating. We have a function that is calculating a sum of columns in an array. So we have some arrays, a matrix, We have a matrix, and we are calculating a sum of columns in our matrix. So we have matrix X, R is number of rows, C is number of columns, and for I in 1 to C, so we are iterating over columns, and then we're iterating over rows, and for each column we calculate the sum of a column. Okay, very simple function. And this function can be easily be done multi-threaded. So instead of having all column sums being calculated in a single thread, what we could do, we could tell Julia that each set of columns or each column will be simultaneously calculated in a separate thread, because it just aggregating sum, and one worker doesn't know about the other. So one thread can calculate the sum of column 5, and the other thread can calculate the sum of column 6. They do not need to exchange any information, so this is easy. Since all threads are seeing the same memory, all of the threads will be seeing the variable x, and all the threads can write the result to the variable y. So as simple as that, I can just say that this loop is multi-threaded. So there is a special macro threads.addThreads that is causing this for loop to be multi-threaded, so to be run simultaneously, so to be divided onto several threads. This macro is looking at what is the number of execution. So here it's having a look what is the number of columns, and then decides how to distribute the workload over all the threads. But it's happening automatically, and we are very happy because we don't need to program it. Okay, and so we have the first implementation of the function, and we have the second implementation of the same function. Now we want to run some tests. So I'm creating a matrix which is 1000 by 1000. So this is a matrix of 1 million elements. Just for example, we could try different sizes, and I'm comparing the execution speed. Now, for the first time, you run it, as you can see here, you have some compilation time. So here I'm doing time benchmarks, and I'm doing time benchmark twice because the first it takes compilation. So you can see there most of the time was devoted to compilation, and I'm looking only on the second value. So you can see that here it was 0.7 millisecond and here was 0.5 millisecond. Actually, it might not be, it will be, how good a result am I going to get via parallelization? It strongly depends on the structure of the data. Okay, but you can see it's faster. It's faster. So using the code running with threads is like 40% faster. Let me try maybe to run this once again. Probably those results could be different. But basically the multi-threaded code is much faster. On the negative side, it's using more memory because it needs to spin those threads needs to communicate and so on. So more things are happening. And of course, the speed up is going. Is going to depend on the exact size of the data. So maybe we have, for example, more rows. We could see what's going to happen. So now I have used a matrix that has 10,000 rows, and this time you can see the speed difference is much more significant. Okay, so this time you can see that already multi-threaded code is 4 times faster. Basically, your results will vary but running 8 threads, expecting that the code runs 4 times faster is a reasonable assumption. It will though strongly depend. It will strongly depend on the structure and size of the process data, because there is always some overhead with regard to multi-threading, because still you need to parallelize the computation. Now, using threads, it's tricky because you are doing many things at the same time. So if you are doing group projects, you know that having a group of people working on the same thing requires some coordination, or all is in vain. And similarly is with multi-threading. So let us consider the following simple code. Again, this is quite a simple piece of code. It's named fbed, so I guess you know you can expect something not very good. So we start a variable x that is equal to 0. And then what we do for 1 million times, we're going to increase x by 1. But we do it in multi-threaded way. So we employ all those 1 million threads to increase x 1 by 1. And now there is a question for you. What do you think? What result we are going to get? Any guess? So what we would like to get? We would like to get 1 million, right? Because we are increasing x 1 million times. So this is what we would expect. Let's see what we get. We got 126,173. It's not million. I have 8 threads. It's roughly 1/8 of a million, but slightly more. Let me try to run this once again. This time I got 125,955. Let me run this once again. You can see each time I run it, I get totally different result. It's totally non-deterministic. And each time I run it, it's roughly slightly above 1/8 of 1 million. So what is happening? Namely, I'm increasing x here by 1. But what does it mean to increase x by 1? It means I need to take the value of x, calculate x plus 1, and then assign it back to x. But it takes time. And other thread at exactly the same time might have looked at its old value of x and assigned it back. Okay, so here we have a situation that the threads are racing for the same value, and they are using all the values of x, and it totally does not work. This is a very common problem. This problem is, of course, in most complicated code. And you can also see that this problem might be very hard for debugging, because each time the result is wrong, but also each time the result is totally different. So you are really started to check your sanity, and you start to wonder what's the hell is going on, what am I seeing? Okay, so now how to correct it. So now we see the problem and how we can connect it. So basically, we need to provide locking. So locking is a mechanism that I'm saying to a block of code that it cannot be modified by something else. This is one option. So one option is locking, and the other option is atomic variables. Atomic variables is a special type of variables supported directly on CPU level, so on your computing core, on your computing processor, that atomic variables CPU, your processing unit, controls that only a one thread can modify or read that atomic variable at a time. So you have two options. Either you can use Either you can use atomic variables, or you can use locks. Okay, so let us have a look at atomic variable, how is it going to work. So here we are having a function named fatomic. So how does it work? I'm creating an atomic x value. So I'm saying x is now thread's atomic int. So it's an atomic integer value. It has some default initial value. This is how in Julia we are accessing references. So this is actually a reference to a value, and to access the actual value, we need to do x and square bracket. Also, this was in the web server, but then I didn't discuss it because there might be happening some things in parallel. So just in case, I also use the reference. So this is the reference. This is how you dereference the value. So x is a reference to integer value, and this value is an atomic. And now once we've done it, we have a special operation which is named atomic add. And the atomic add operation is taking x and increasing its value by 1. Okay, and now we have still the same loop. And this loop is happening in parallel, but since x is not a normal integer, but it's an atomic integer, CPU, the processor, controls that only one thread at a time can modify x. So obviously what it means in practice, that it's going to yield a correct value of 1 million. Okay, so you see we got the result we were waiting for. So this is the first way to do it. So you can have special atomic variables and have CPU control it. Now the problem is that there is a limited number of operations you can do on atomic variables. It's not so flexible as one wanted to do. So if I click tracks.atomic, there is also only a small list of operations you can perform on atomic variables. Okay, so it's not very convenient to write complex operation, or it would require some other tricks. So for more complicated operations, you can use the mechanism of locks. So basically what locks do, locks are used to define a block of code that is devoted only to one thread. So I can define a block of code that can be executed only by a single thread. So how do I do it? I first need to create, yep. Yes, for this function, of course, for this function, of course, it would be faster to just add everything because it's much simpler code. And actually, this is a funny thing about Julia. Let me show you. Function f_add. Let me write a function like this: x equals 0 for I up to 10 of 6. Of course, these are toy examples, so they are too simple. But if we do function like this, we yield x, and let us measure the time of this function at bit time f_add. So actually, for function like this, suddenly the execution time is 2 nanoseconds. It's basically 0. And let's see up to the time of 7. Let's see what's going to happen. You can see it's still the same time. Why? Because functions as simple as this, compiler can understand what is going on. Julia has very clever compiler. Let's see what compiler is going to do to that function. Add code native f_add. Blah, 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 blah. Maybe at code lowered, we'll see it better. Basically, what compiler does, it's here in the code, but it's, let me see, code lowered. No, it's still adding. Yeah, it's adding. So basically, what compiler is going to do is going just to analyze this code. I'm not seeing it here. It's somewhere here. Oh, it's here. It's analyzing the code, and it just knows it needs to yield million or 10 millions. And that's it. Okay, so the compiler can understand this code that it's deterministic. It needs, in this case, 10 to the power of 7. So it needs to yield 10 million, and then just replacing the code with 10 million all. Okay, so of course, this is also a problem of micro benchmarking, because you cannot get a loop faster than this one, because just compiler solves the loop. So Julia has not. So the Julia compiler stack can be quite clever at moments, but putting that aside, uh, uh, of course, in normal scenarios there would be more operations than just adding number. This is just the most basic hello world example for parallelizing this type of computation. So hope this answers the question. So now we are having a look at logs. So with atomic values, we can only perform simple operations. Sometimes this is enough. Very often it's not enough. And we want to log a block of code. We want to log a block of code for other threads. So this is something we often do. That we have a block of code and we want to perform logging on a block of code. And this is easy to do. So we have threads log. So we can attach a log. We can attach a log to a block of code. It's easy as that. Threads log do. And here there can be any block of code. And now I'm sure that Julia controls it, that only one thread can execute this block of code at a time. Of course, again, normally this would be more complex code, and usually you try to provide a log mechanism to a small part of code that is only possible, because it slows your code down. And especially this, it means basically that this part of code is not multi-threaded, because only one thread can execute this block of code at a time. And now, depending on how big this block of code is, you might either want to use spin logs for blocks of code that take very short time to execute, and you also do not want to immerse one logs in others. You would be probably using spin logs. For bigger portions of codes and for more complex code, and also if you want to immerse one logs in the other, and for more complex architectures, you might be to want to use reentrant logs. So as of today, they are by standard, of course, it's possible to implement more log types, but by standard these are spin logs and reentrant logs implemented in Julia. The logging approach to logging is almost identical. So you can see that we are having here very similar codes. And basically you have here the logging mechanism. And now here is a very small test. So we have a function that yields the bad results. So we have a function that yields the better results, the atomic results, the spin, and the reentrant, and we run each of them 2 times just to have the measurements and collect the results in the table. So here we have the value, and of course we want to have 1 million, and here you have execution times. And still the execution time for atomic function is the execution time for the atomic version is much faster than anything else. And the reentrant logs are relatively slow. They are more for big portions of codes. And big portion, I mean the code that takes a longer time to execute. On the other hand, spin logs. So spin logs, when there is a spin log and nothing is happening, it could eat CPU power. And a reentrant log is just waiting. So there are small nuances which log ones should be applied. So now we move to the next. Now we move to the next part, which is multiprocessing. Okay, So multiprocessing and distributed computing. So there is so now what we want to do is not to use several threads within a single process, but rather than that use several processes. So we have in Julia we have a special module which is named distributed. I can add distributed is creating a Julia cluster. Julia cluster can consist of processes which are local to this machine. So this could be a bunch of processes on this machine, or this could be remote processes at other machines, at other servers. So the command add procs is adding processes to my machine. So actually I should see now that I have several Julia processes running. I'm not sure how good am I going to oversee it. Oh, I do not know which is which now, but basically I have one master Julia process and 4 slave Julia processes running under this master. So I can list those processes. Oh, I have even 5 somehow. Okay, let it be 5 processes. So I have I have 5 workers because it's adding up to 5. Okay, so I have 5 workers running, and they are enumerated by 2, 3, 4, 5, and 6. Okay, and I have also the main process. I have also the worker number 1, which is this Jupyter notebook that is controlling the other processes. So Jupyter notebook is running in the main process, and I have 5 workers. Okay, and a total of 6 Julia processes in my cluster. So I have constructed a cluster. So now this cluster can be used to perform computations. And again, similarly, what do we do better? We have again some simple micro benchmarks. So this is a function that is adding how many 100 million random numbers. So it's just generating 100 million numbers and adding each to the other, and it takes half a second to run. There is some is less interesting, okay? But it's taking one. Am I right? 100, yes, 100 million random numbers, because it's 10 to the power of 4, and here it's 10 times 10 to the power of 4. 100 million numbers, and this is adding it to each other. Okay, simple as that. And similar to what we did later with threads, we can distribute that loop over processes. So we have this module distributed, or maybe I've loaded it previously. I have already some amount of workers. So all I need to do, I need to provide a distributed macro. And what this macro is saying that this workload should be distributed. Now, usually I need some aggregation function, because I need to decide how to aggregate the results of this multiprocessing computation. So here I will be adding, but probably one of the most common scenario is aggregating rows of a data frame, which I will show you in a second. So here I'm adding the results, and I'm saying for 1 in 1 to n, and what is going to be added is the last line. So I could have many lines here, line 1, but the last line will be added. Okay, so whatever is in the last line, this or aggregated, I wanted to say, whatever is in the last line is going to be aggregated, and then I get the results. So now if I'm going to run it, now I'm benchmarking this twice, and what you can see, the first time it took a significant time to run, and most of this was compilation time, because I have a distributed system and I needed to communicate with the workers. And whenever you do something distributed, you always need to expect that, you know, if you send code to the workers, then the workers need to compile this code, they need to prepare, this needs to be synchronized, so it takes time. Okay, so the biggest disadvantages of distributed computing, of course, if your computation is big enough that it covers the time required for communication. Okay, you are seeing this works. The next time I run it, it might be faster. Now it's even faster because the code got compiled and the connections are open and so on. And so you are seeing it was like in a single process mode, it was like 0.48 seconds, and now it's 0.20. So it's roughly twice. So it's roughly twice as it's roughly twice as fast. Now this can be used for slightly more complex task. We have multiple. We have here multiple processes. So what we could have, if I'm going to look at those processes. Where is this? So before I run this code below, I wanted to show you something. We have multi-processes. So I could decide that I want to run something at a given worker. So I've been showing you that I have several workers. So this was workers. So I had workers 1, 2, 3, 4, 5, and 6. So for example, I might want to run on worker 3 something like maybe something something maybe okay, something very simple for a minute, and in a second something more complicated. So I might want to run on worker 3, 4 plus 3. If I run like this, what am I getting? I'm not getting a result, rather than I'm getting a future object. So future object is a promise of execution because I have submitted a job to a remote worker and now I'm getting a promise of execution. So if I want to rather get it, I need to use a command fetch. And the command fetch is going to bring me the result of remote worker or bring an error. Because if computations of remote worker have failed, I won't be seeing anything nice here. Okay, so what about functions? So suppose I have the functions, the following, function f, and these functions could be doing something like println I am on worker. And here I'm going to put my ID. My ID returns the number of worker. And let it yield some random value just for fun. Okay, function like this. So I can run this function. I could type f. And of course, I am on worker 1 because the master worker, my Jupyter notebook, is worker 1. So let us see what's going to happen if I try to run this on remote worker. If I just do spawn at, this time maybe worker 4, f, then all I'm getting is the future object. So I would rather need to fetch the result to be able to see anything. Okay, so let's try to fetch. Let's see what's going to happen. I got an error. F is not defined on worker 4. Why? Because each worker is a separate Julia process. This means that each worker has a separate process, so it has its own set of libraries loaded, own memory, and own set of functions it sees. It's a separate Julia program. It's totally different, something like we had with threads, when we could see that it was variable x, and it was seen by all threads, and they could even, you know, fight for this variable x and mutate it at the same time, and we had these locking issues and so on. And here is kind of different thing, because you can see that this function is not seen by other worker. What we can do? We have a special macro at everywhere that you use quite often. And what macro everywhere is doing, it's going to define that function across all workers in the cluster. So we have a cluster, we have a group of processes, and we want to say that we want this function to be known on all workers. Of course, I could use spawn at and define the function on a select group of workers, but usually in most applications, we end up, having the same set of function on all workers in the cluster. Usually this is the most convenient situation. So this is what am I doing now? So now this function has been defined on all workers in the cluster. So let's go to see now what's going to happen if I run on worker 4. I'm seeing here the standard output. So the result of println instruction, it was called on a remote process. But those results, so the standard output of the remote processes, are being by the Julia cluster, by Julia distributed mechanism, automatically directed to the standard output of my process and decorated by this few space characters and from worker 4. Okay, so this has been added by Julia distributed module, and this is the output that has been generated by the remote worker. Okay, let us think what's going to happen for some more complicated scenario. Namely, there is some pattern on how to perform processing. So let's assume we have to do some kind of computations. Again, this is a toy scenario rather than real use case, but let us assume that you do some hyperparameter search. So you have two parameters, I and j. So we have two parameters, I and j, and you have some set of values for those parameters that you want to iterate over this class, or you want to iterate over several Julia processes. So let's say I have the parameters here, so they would be here. So I have two parameters, I and j. I is from 1 to 4 and j is 1 to 5. So I have a set, so this is generating me here a set of all possible values, 20 values for those parameters. And for each combination of those parameters, I want to run a computation, but not a single process, but I want to spread out it to all processes in my Julia cluster. Okay, is that clear? So I have a set for parameters I and j, and for each of set of parameters, I want to do some computations. That could be, for example, different parameterizations of a deep neural network. Again, this is a toy code. You could insert here a code from flux.gl like Sebastian was using on mlj.gl, but you have a set of parameters and you want to train a machine model over that set of parameters. So what is here is typical setup for such situation. So what do you want to do? First, you of course need to load the distributed module. So you are loading the distributed module. Now, probably you have some project environment defined. So you have downloaded, when you have downloaded the course materials, there was this project.tom file that defined project environment. When you are running a cluster, you want probably to define the same project environment for all Julia processes running in a cluster. So each process needs to have the same state. It's quite not obvious, so it sometimes yields questions on Stack Overflow and other places, because people sometimes are adding processes to the Julia cluster, but then child processes are running in different environment, in different environment than master process. Usually you want to have the same environment. So what you do, across all processes, you load pkg, so the package manager, and you activate the environment for each process. Now, for any type of processing, and then you could be adding here flux.gl, mlj.gl, or other data mining libraries. For each process in the cluster, you are loading a set of libraries that is required for computations. Then you have some function that is performing the actual computation. Perhaps training a model. Again, I'm using here hello world functions just to have the code concise, but this could be a function that is training a machine learning model. Then the next thing you have, usually you have some code that you want to init on each worker. For an example, each worker at the beginning of computation could load the data from a CSV file. Again, here are stupid examples, so I'm just here initializing the random number seed, but actually it's useful examples because sometimes I'm doing Monte Carlo simulation over cluster, so I'm very often having a code like I have 1,000 workers, and at the beginning of computation, I want to initialize the random number generator. So this is the function that is initializing. Perhaps it could be also reading CSV file and doing other stuff. So this was all in other course material, so I didn't want to, I didn't want to complicate with things that you have already seen. So this is the initialization code. And then what you do, you usually want to initialize, so for example, load CSV files on all workers in the Julia cluster in parallel. So this is a very typical this is the very typical code scenario. What you do, you want to synchronize in the end for each worker ID in the workers in the cluster. Asynchronously, you spawn the process of initializing that worker. Why do it asynchronously? Because you want at the same time to open connection to all workers in the cluster. If you have 5 workers like I have here, it doesn't matter that this loop has sync and async. But if you have a cluster with 2,000 workers, it's the difference whether this loop is going to be completed in half minute or half an hour. Okay, so this is so in production system this makes really a good pattern. So this is the code. Now you can see that each of this worker has activated the project. So now I'm making sure. So now this is the folder. This is the folder of course materials this time. So now I know that each worker has the same virtual environment. So each sees exactly the same set of packages, and this is good when you want your workers to cooperate. You don't want 2 workers load 2 different versions of a Julia package. It wouldn't be good. Okay, we have all those workers. And now the next step. So here I have, so iterator's product is a Cartesian product of those 2 parameters. So doing a Cartesian product of a set of parameters is something very common when you do parameter sweep. Now I've noted I needed to convert this to a vector because this is what a distributed can understand. So distributed macro is expecting here a vector, and it also must know all the values, at least the amount of values, to be able to distribute the workflow. So I'm using here a Cartesian product, then collect is materializing this Cartesian product, and vec is presenting it as a vector rather than a matrix. This is not a big deal, but this has worked for me very well in many scenarios. And since this is a vector of tuples, I can iterate a tuple out for it. So basically, it iterates I over 1 to 4 and j over 1 to 5. So this is like a nested loop. But I wanted to write this nested loop in a single line. So I want to do the distributed macro to distribute all workflow. And now, typically, when you do some computations, you usually want to have results in a data frame. At least, again, this is my experience. I usually want to have a result in a data frame to do it for further processing. So this would be a typical, again, scenario. So here I gain some random values. I'm generating value A, I'm generating value B. Maybe you are calling some functions that performing the computations, performing your computations in your Julia cluster. Then at this last comment, it yields a data frame. And it has also, this comment has also nice syntax that I can provide. This is syntax from named tuples that works nicely here. I just provide the variable names, and it will generate columns as matching those names. Only I want here the process ID. So usually when you are yielding something for aggregation in the distributed environment, you want to have also the process ID. So you know where each value has been generated in the Julia cluster. So that's why here I'm having this process ID. And what is going to happen? So I'm going to get a data frame where each set of rows has been calculated in a different worker in the Julia cluster. So you can see this was the worker number 2, and those rows were calculated in worker number 2. This was the worker number 3. This was the worker number 4, worker number 5, and worker number 6. So you can see how this computation has been distributed over the entire and over the entire Julia cluster. Now I've designed this code to be like a starting point for any distributed computations that you could typically make. So this is if you do any parameters sweep in machine learning, any type of processing. This pattern has worked for me many times. So this is basically from my experience of running this distributed models. Now going to slightly more even complicated scenarios, sometimes you want the processes to communicate in each other, and sending the data across Julia processes running in a cluster is kind of tricky. There are currently new libraries under development, but one possible library is a parallel data transfer. And here would be a small use case scenario, but perhaps I'm not going to discuss the code in the detail. But rather than that, have only a small comment. So here, what am I going to do? I'm going to parallelize a concept of cellular automaton. So maybe it's not so big to be parallelized, but anyway. So a cellular automaton is a type of computing. Say it's a kind of bacteria. And here on the first line, you have first generation of bacteria. So if I have 3 bacteria, the one in the middle has no air to breathe and dies. If I have 2 bacteria aligned like this one dies. When there are 2 bacteria and empty space between them, a new bacteria is born. When I have 1 bacteria like this and empty space, a new bacteria is born. Here, a new bacteria is born or survives to the next generation. Here, a new bacteria is born. So this is a kind of bacteria colony. And what we have here on the y-axis is time, from the top to the bottom. So this is first generation of bacteria, second generation of bacteria, third, and so on. So some very simple simulation. And what am I going to use? Distributed mechanism. So this is a sample code how to parallelize this kind of computations into multiple processes. So the state of computation is presented as a vector. And if you look at this rule on how bacteria can survive to the next generation, I need to look only on 1 field away on this board. So this is a kind of long vector. And all I need to see is to have a look only 1 field away. So actually to calculate, yep.
Or it's just because then the pattern is nicer?
So there are many. So this is rules 30. And there are many such rules you can. There are many such rules you can choose from. I do not. So I guess most of those rules have some story, but I do not remember the story behind this one. So, but this is. Yeah, there are many, yeah, exactly. There are many of those rules, and each 256. And so this one generates nice. This one, I choose this one because it generates nice specific pattern. But there could be story. The point is. The point is now that only one spot away needs to be shared in the cluster. So basically each process can see vector and only one cell needs to be exchanged between processes. And it means if I have cluster for this type of, if I have a cluster for this type of computation, I need to write a code. So what I need to write, what I need to write, I need to write code for rule 30, and this is a short piece of Julia code. And I need to write a piece of code in Julia that is exchanging this border information. So so basically at each generation of a loop, two things need to happen. First, I need to copy border cells between the processes. So I need to copy the information in border cells, and then I need to calculate the state of simulation for the next generation. So you have code. So you have code in the Jupyter notebook. So let me try to run it. So here I'm loading the distributed module. This is the function that is evaluating rule 30. Here I have the function. Here I have the function that is setting and getting the border. Below I have function that is printing that, and basically this is the line. So at first I'm initializing all the workers. So what I need to do, I need to fill in all information with false. So I make all empty fields, but I start with a single bacteria. So I have single bacteria to start this bacteria colony. I have some Boolean variable whether to print this to standard output, and then for each step, I'm exchanging the information about the border cells. So this is one thing to do. I need to exchange the information about the border cells so the bacteria know their neighbors, and then on each worker independently, I need to apply rule 30. So here you are seeing this sync async loops because I'm doing something on each worker in the cluster. So each worker in the cluster has the information about state of bacteria that they own, and they only need to transfer the border information. So if those states were very long vectors, then of course it could increase the computational efficiency. And if I run it,
it is so important that on the border is exchanged.
okay, because if I need, why is it important? Because if I needed to exchange everything, I would each worker need to keep all state in the memory. And for a large scale simulation, a single worker might have not so much memory. I have actually, but without a source code, the final comment for a larger scale similar scenario that I wanted to comment on. Let me just and I think I should have I should have even a number of workers for this to run. So I click probably something too many times. So let me add one process to the cluster and try to. Yep.
So I don't get played too much with implicit global grid, but I assume that I don't know if you're familiar, but I would imagine that with implicit global grid, the code would look much shorter and prettier than the parallel code. You know about the implicit global grid package? The one where you.
Oh, then you have this grid. Okay, yeah. It might make using this pack. I do not know this package, but I know what you mean. That you have this grid defined. Yeah.
Therefore, you don't have to write all the side code, which kind of.
Yes, because here I needed to implement. So here it's like I implemented it myself. Yeah.
Global grid.
Yep.
as opposed to having the common mechanism.
Yes, this could be used. This could be used perhaps to make the code simpler. And here just plain here is just plain vector and plain Julia code. I've run it earlier, and I'm using here some constant global variable, so it's slightly complaining. But here it is, and we are getting this pattern. I have been also trying.
Global grid could be problematic in this case. You would need to use flip-flop with implicit global grid. And I understand that, Przemysław, you are doing an in-place update, right?
Yes, I'm doing here in place update. I would need to, I would need to check how to update it.
So what I mean by the need of the flip-flop is the fact that because Przemysław is doing the update in place, if I understand his code correctly, he has to separate the synchronization step from the update step so that each worker can safely update itself without caring how fast the other worker updates itself. And that, because otherwise, on those borders, you wouldn't be sure if you update in place if the other worker actually did what in sync what you do.
Yeah, so I'm doing it exactly like it's minus n and n, and it's 1 and 2, and I'm changing so they can do it simultaneously.
Yeah. You would need to do this flip-flop, which means you actually keep two grids.
Yes.
And do not change the first grid, but just compute the second, and then you can do it safely in parallel, and then just change the destination.
Or I needed some other variable to keep all the border. Okay, I could keep it. Yeah, I could see it. I could keep the border in a special cell and have a set of cells for the border. Yeah. So anyway, since this update exactly at this code is happening in parallel, and this happens exactly here, so I need to handle somehow this parallelism. So last but not least, the same syntax can be used to build Julia clusters. And basically, Julia clusters can be run on AWS Spot Fleets or Cray supercomputers. All is needed to build a Julia cluster is to configure passwordless SSH, which is relatively easy to do. You have this in the slides. There is already I already ran out of time, so I'm not going to show that. But you can run a passwordless SSH Julia cluster, and just out of curiosity, I've been using it to run a very classical shelling segregation model. So this is two types of agents. One have red political views, and the other agents have blue political views. Everybody wants to live in a neighborhood with similar political views, so they do not like people of opposite political views, and they need to relocate. And then you have a border level. Then you have a border level like this one, and with exactly the same approach. I have been trying using either AWS or Cray supercomputers to scaling these computations up to several billion agents running on a machine up to 4,000 CPU. It was even tens of billions of agents running up to 4,000 CPU cores. And in Julia, with this approach, you can. So this is something really that really scales well. And I could so this shows results for the so-called weak scaling. So I've been increasing the problem size and observing the speed for ever increasing problem size. And I could see that really a piece of such Julia code, so the Julia cluster can run on a machine on several thousand nodes. Yep.
Question. I'm definitely going to check out your course notes. I'm wondering whether they cover elastic scaling, or if it's something that's there's a good package for that.
But which scaling? Sorry, I misheard the beginning.
So asking for more instances from one.
Of asking from instances from EC2.
Like from one instance.
Oh, you mean elastic scaling?
Yeah.
Okay, so in case of Julia cluster or Julia distributed, basically, it's very easy to add instances to the cluster. It's kind of tricky to remove instances from the cluster. It is possible, but it's easier to add. It's easier to increase than decrease if you are talking about the same running cluster. Like at least this is from my experience. This is still being improved with Julia, but basically it's easier to scale up than the scale down if you are still in the same cluster, because of course you could shut down the cluster, rerun it, and so on. But usually what I've been doing, I've been spinning up a spot cluster and then using it as big as it was. And sometimes I've been running computation. If it was a spot cluster, sometimes some nodes failed. If it was, for example, a parameter sweep, then I wrote a code that was, for example, re-evaluating for some sets of parameters computations. So basically, if you adding nodes is easy, decommissioning nodes, if it's a running computation in the middle of the process, you need to start asking yourself what is happening with the data in memory if you decommission a node. So it's always tricky. Okay. So this is what has been discussed in the last module. I told you about the homework at the beginning, so I'm not going to repeat the homework. But anyway, you have this also in course materials. In the course slide, the time for the homework is 1 week. And just to conclude what we have been discussed today. Different parallelization options, although without GPU, because there is no time to even further talk on that. So our workshop is too short. But I have looked today into SIMD parallelization, so single instruction, multiple data. We have had a look at green threads and how are they related to I/O blocking. I've been talking a lot about multi-threading, and especially we have also discussed the locking mechanism, the chase for parameters, and we've talked about multiprocessing, mostly about single machine, but you need to be aware that the same API can be used for distributed clusters, and more information on Julia in distributed clusters you can find in the course materials. So thank you very much, everyone, for attending this workshop. This was really big pleasure for me. I also had this pleasure to tell you the first lecture, the opening lecture, introduction to Julia of this workshop. And now I'm finishing with the closing lecture, unless somebody wants to add something. So thank you very much.